10 times, however many times, get negative 1 over RA as a function of that's not right. Conversion, sorry. Oh, I left something out, sorry. Pick a conversion first. That's how you get the temperature coming out of the reactor. Yeah. And so you can do this and then integrate under the curve. So there's your CSTR, right? Or I mean a PFR. And then a CSTR would be. But you guys don't have to do it that way. It's just time consuming and monotonous. And I think it's just as much grunt work in Excel as just solving the damn thing numerically. But know that the option is there. The Levenspiel plot allows you to avoid solving the differential equation. It always allows you to avoid solving that differential equation. All right, so let's look at an example. And again, we're just going to set this one up. We'll probably be done a little bit early today, but I don't think you'll complain.
Exam week.
Is this another exam week?
Yes, exam today and tomorrow.
Today and tomorrow?
Yeah.
Well, I'm glad we went on the 11th. At least it was, I thought I was really late, but I guess everybody's late. Well, some of these I'm sure it's just one exam per semester instead of two. No, what I mean is though, like one midterm.
Only one of them, the other one has three.
The other one has 3 just like mine and they're going this late? Yeah. They're just going to give you like back-to-back tests at the end of the year? I mean, I'm basically doing that.
Wow. Thanks for,
Hey, it's on the syllabus. It's just hard to give a test in this course until you guys have seen at least, I don't know. Maybe I'll change it in the future, but I inherited the strategies that I'm using. All right, so we have a PFR, the reaction A plus B goes to C, irreversible, everybody's favorite. And we're given that the conversion is 85%. We want to know the volume necessary. And how do you about it? Okay, so material balance or design equation. Right? Rate equation, let's assume that it's elementary. Right? No questions there about where that came from? Okay, stoichiometry. What a cop-out. The problem that we're doing when we go through this, that's from your homework, is not liquid phase, so at least you guys will have seen it. Okay, so stoichiometry, liquid phase, so that makes this part easier. You just get, so the volumetric flow rate, we ignore changes in it. And so the concentration of A is equal to the concentration of B. Why is that? Because they come in at the same flow rate, right? And they're both reacting at the same rate. And they're both equal to Ca naught times 1 minus x. Again, it's pretty simple when you have a liquid phase reactor. Okay, so then we combine. And so you get dx dv is equal to negative k times concentration of A naught squared 1 minus x squared. Why is it squared? Yeah, because the rate equation is Ca times Cb.
Why is it negative?
The design equation is, no, sorry, you're right. Where did I mess up? I just missed it. You're right. And then what is K? It's not constant anymore. Okay, are we done? What's the other equation that we have to use now? The energy balance.
It's volume. Or volume discusses.
So which form do we want to use? Temperature is a function of conversion. Why?
So we have to. We have to. So.
Do we know the conversion? At least on the outlet. All right, so temperature as a function of conversion, we get delta H reaction at the reference temperature.
That's same equation, same things.
Yeah, we're up to 6 now or something. And we're told for this problem, what do you think we're told?
Delta CP equals 0.
Delta CP equals 0. Patty cake easy, this one. T0 plus X times Okay, so I have temperature as a function of conversion. You could try to plug that into here, and this into here, and try to solve it analytically. Do you think it would work? No, you're not going to be able to solve that differential equation analytically. So instead, you use some mathematical method, and like I said, we'll talk about it. We're going to do it for a harder problem, but we'll do it in Excel. And you solve those equations simultaneously. And what you end up with so where does this one stop? Why? Because it's irreversible. So if you hear the word irreversible, that just means that the equilibrium conversion is equal to 1. And this is often referred to as the ignition point, because it'll also be over here. When you're plotting, you can also plot temperature as a function of volume. And what temperature do we start at? Whatever T0 is. What temperature do we end up at?
Are we saying it's volume goes to infinity?
Yeah, if we had an infinite volume, it would just be T0 plus 200. But of course we didn't. We said something like 85% conversion. So wherever we are here, 0.85. That's the volume needed. And then that corresponds to some temperature that's less than temperature plus 200.
So is that defined as the ignition line, or I thought you said ignition point?
Yeah, I mean, usually they'll refer to it as like the ignition temperature.
Okay.
But there's not, I mean, depending on the field you're in, there'll be specific definitions. But it's just the temperature at which the reaction starts to sort of take off. Yeah, starts to accelerate.
So those should correlate accordingly, like obviously as conversion is increasing, volume is gonna increase. So it's like if we put the graphs over each other.
Oh, yeah. Yeah.
Okay.
I mean, temperature is directly related. I mean, it's just
Yeah.
that, T plus 200x. So the temperature and the conversion are directly related. That's the only reason why the temperature is changing, right? It's because we're doing a reaction, and for every little bit of reaction that takes place, we're either releasing or consuming heat based on the delta H of reaction. So the volume that you get for this particular problem is 305 liters. What volume do you think you'll get for a CSTR? Higher or lower?
Higher, much higher.
Much higher. Anybody want to try again?
Oh, well.
Why is it lower? It's 175 liters. Why is it lower? Yeah. Because the CSTR operates entirely at the outlet temperature. And what type of reaction is this? Exothermic. Thought so. Yeah, T plus 200x. So even though